the cardiac cycle, the valves opening and closing, and the heart sounds, which are made by the valves closing. So when valves close, they make a sound. When valves open, they don't. So what we're going to do today is we're really going to start getting into cardiovascular function. In other words, how does the whole system work, and what makes what keeps the heart working in favor of homeostasis. All right, so a very important concept to go along with the heart is this idea of cardiac output. Clinically speaking, this is what we care about in terms of what is the heart doing. And that's because the heart's principal role in the body is to move blood around. Without that circulation pump, the cardiovascular system can't do its job, which is to deliver nutrients and oxygen and then pick up waste products and carbon dioxide. So one of the principal factors in that is how much blood the heart is moving per unit time. So we call that cardiac output. And it's typically it's given in liters per minute. So a volume per unit time. So how do we calculate that? Well, it's very simple. It's just heart rate times stroke volume. Okay, so this is a new term. What is stroke volume? We're going to talk about what stroke volume is more in a minute. But essentially, it's how much blood the heart moves in each beat. So each time that the aorta and the pulmonic valves open and the ventricles contract and they push blood out of the heart, the amount of blood that is pushed out in that beat is the stroke volume. So if we take the amount of blood per beat times the number of beats per minute, well, we're going to arrive at a cardiac output of liters per minute. So typically, the cardiac output is about 6 liters per minute, or 6,000 milliliters per minute. And that assumes a heart rate of 75, which is a very normal heart rate, and a stroke volume of 80 mLs. So we're going to see cardiac output play a major role when we start putting the blood pressure picture together, which we may do in class, or you'll certainly do it in lab. When you do your blood pressure lab, you'll start seeing how some of these factors sort of intermingle. All right. So in order to create cardiac output, the heart has to beat in a coordinated way. We have many, many heart cells, myocardial cells, and they all have to sort of beat at the same time, they have to contract at the same time if the heart is going to function properly. So the heart has a built-in system for that. In skeletal muscle, the nervous system has to stimulate contraction, right? For skeletal muscle to work. For the heart, it's a totally different system. The brain doesn't make the heart beat. The heart beats all by itself. It contracts in a rhythmic way all by itself. Now, the brain can affect the speed of the heart contracting, which we'll see in a minute, but there isn't a nervous system per se. So instead of a nervous system, what we have to coordinate the contraction of the heart is this conducting system. And it has multiple parts. The first part is called the SA node, or sinoatrial node. It gets its name from its location. The coronary sinus, remember, drains blood from the coronary arterial circulation into the right ventricle. So the location of the sinus is right about here. So this spot of the heart, the sinoatrial node, is near the coronary sinus. And we typically refer to it as the SA node. It's critical because this is the normal pacemaker of the heart. So the region of the heart that triggers heartbeats is usually the SA node in healthy, normal people. So it's sort of the beginning of the conducting system. So from there, we have what are called internodal pathways. All right, so it's important to understand that there are two kinds of cardiac cells. There are the contracting cells, and then there are the conducting cells. So if you were to look at the heart, the vast majority of cells that make up the myocardium are contractile cells. In other words, they're cells that are going to reduce in size when they're stimulated to contract. But in addition to those contracting cells, there are some specialized cardiac myocytes that instead of contracting, they simply conduct electrical impulses or conduct an action potential. So the SA node, for example, is made up of those cells that don't contract. Instead, they just generate action potentials. Connecting the SA node with the next part of the system called the AV node are these little bundles or tracts that pass through the walls of the atrium. And here again, these are made up of non-contracting conducting cells. So they're cells that are just passing on a signal, so to speak. And even though in our picture here they're only shown in the right atrium, they're present in the left atrium as well. So the SA node fires, and that signal passes through these internodal pathways. On the way, they're going to stimulate the atria to contract. So the signal for atrial contraction is that electrical impulse passing through these internodal pathways. All right? So then the signal arrives at sort of the center of the heart, and that's called the atrioventricular node. Atrio because it's near the atria, ventricular because it's near the ventricles. So the way I always think of the AV node is it's at the center of the heart because it's between the left and right, and it's between the top and bottom. It's between the atrium and ventricles and the left and right side. So the AV node is sort of the center of the heart, and its role is it captures that signal that's passing through these internodal pathways, and it holds on to it for a little while. Now, why is that important? Because the atria need a chance to contract before the signal goes out to the ventricles to contract. So in a perfectly working heart, we want to see the left and right atria contract, a little bit of time passes, and then the left and right ventricles contract. So the delay, it's called the AV nodal delay, that occurs at the AV node allows for that to happen, allows for the atria to contract first, and then the ventricles to contract. All right. So once that time has passed, the AV node releases that signal, and then it passes into the rest of the conducting system. All right. So going down through the interventricular septum, right? So here's the left ventricle, right ventricle. A septum is just a wall. So the interventricular septum is the wall between the ventricles, right? That signal goes from the AV node and it starts to course down into this wall. Now, the first little bit of it, which is right here, we call that the AV bundle. And then that AV bundle splits here, and it becomes, and we get bundle branches. So the AV bundle used to be called the bundle of His, H-I-S, and you'll still hear it referred to that. So the bundle of His divides, and then we have a left bundle branch, and we have, or I'm sorry, a left bundle, or a right bundle branch here, and then a left bundle branch going down the wall between the ventricles. And then this system ends in these little tree-like fibers or branch-like fibers called Purkinje fibers. So the signal comes down the middle, and then it goes back up, and it distributes, these Purkinje fibers, distribute that signal then to all the contracting cells of the ventricles. So right ventricle and left ventricle. So we go SA node to AV node to bundle of His to right and left bundle branches, and then we end with the Purkinje fibers. All right. So what does that make happen? The conducting system is the triggering system for muscle cell contraction. You know, we want to see the atria contract and then the ventricles contract. So let's take that conducting system and we'll see what it actually does to the heart. All right, so step one is the SA node fires. So it creates an action potential. And the SA node being the pacemaker, it does this, 60 to 120 times a minute, right? So it creates this action potential all by itself. that signal then travels across the atria on its way to the AV node, and eventually that signal reaches the AV node, and then there's a delay. Well, while that signal is sitting in the AV node, we see this spreading purple, right, on the atrium. That's stimulation to contract. So as the signal passes from SA to AV, that triggers the surrounding cells to start their contraction. So we call this depolarization. So just like we saw in nerve cells and muscle cells, as this conducting stimulus is passing by, the membrane potential of the contracting cells flips. So it goes from -70 or -90, and boom, it goes up to +30. So we call that depolarization. And it's the trigger for contraction. So first we get this spreading purple of depolarization, and then what follows is actual muscle contraction. So you can see the arrows here as the atria are contracting. So first they're depolarized, then they contract, all the while that signal is sitting in the AV node, waiting, so to speak. All right. So then what comes next? Well, that signal is released from the AV node. It travels through the AV bundle at first, and then through the bundle branches, so the left and right bundle branches here, and then down into the Purkinje fibers. And as that signal travels, it is stimulating depolarization along the way. So eventually, once it's gone all the way down the left and right bundle branches and then back up through the Purkinje fibers, the ventricles now have been depolarized and are going to start contracting. So as soon as that signal reaches them in purple here, the next step is then they'll start to contract and the heart will start to get smaller. All right. Okay. So the conducting system brings about depolarization, and then depolarization brings about contraction. Right? All right. So let's look at the conducting system in a little movie here. Let's turn the lights. All right, so just to orient you here in the picture. So here's the SA node, here's the AV node, here's the bundle of His, right? And then the left and right bundle branches, and then these are Purkinje fibers. All right, so let's see what happens when we sort of put those together.
Action potentials originate in the sinoatrial node and travel across the wall of the atrium from the sinoatrial node to the atrioventricular node. Action potentials pass slowly through the atrioventricular node to give the atria time to contract. They then pass rapidly along the atrioventricular bundle, which extends from the atrioventricular node through the fibrous skeleton into the interventricular septum. The atrioventricular bundle divides into right and left bundle branches, and action potentials descend rapidly to the apex of each ventricle along the bundle branches. Action potentials are carried by the Purkinje fibers from the bundle branches to the ventricular walls. The rapid conduction from the atrioventricular bundle to the ends of the Purkinje fibers allows the ventricular muscle cells to contract in unison, providing a strong contraction.
All right, so the conducting system of the heart. It comes up clinically, this conducting system, because there are just about a million things that can go wrong with it. So anybody who has a heart that is sick somehow, either from a heart attack or other kinds of disease, very often conducting system problems play a major role because the heart is dependent on it. So if you mess up the conducting system, for example, the heart doesn't contract, the heart doesn't beat. So it's a critical system for homeostasis because without it, the heart either behaves abnormally or doesn't behave at all. So for example, on TV, when somebody's on the hospital bed and they're dying and it goes beep, right? Well, that's a breakdown of the conducting system. When you get that flat line, the heart is no longer contracting. And there are lots of reasons why that can happen, but without this system, there is no heartbeat, there is no cardiac output. Yeah.
Is there a place where you can get this video if you want to watch it?
It should be on there. It should be.
It comes up as a blank screen, And it doesn't
Oh.
play button. Right?
Yes, I know why that is too. Yes, I can send that out. I'll put it. What I'll do is I'll put it on Angel.
Thank you.
It's a Flash file. That's why. Put conducting system vid up. If for some reason I forget, email me and remind me because it's not hard to do. I just have never done that. All right. Next slide, please. Okay. All right. So you can't talk about the conducting system and depolarization without talking about how it is most commonly studied, and that is through the EKG. Have you guys looked at EKGs in lab? You did. Okay. So good. So some of this is a review, this conducting system stuff. The EKG is, what we're looking at there is the pattern of depolarization and repolarization of the ventricles and atria. Now, it's important to distinguish between what we're looking at. So when we look at the EKG, even though the conducting system is making this happen, the conducting system itself is too small for us to see on an EKG. What we're seeing on the EKG is the muscle cells themselves. In other words, not the conducting fibers, but the contracting fibers, because that's what makes up most of the mass of the heart. So what we're looking at here is we have the P wave, the QRS, and then the T wave. And each piece is showing you something different about the heart. So the P wave is atrial depolarization. So in our pictures here, that's this part right here. So this is, at this point, you're going to see this purpling, so to speak, as the P wave. The QRS is ventricular depolarization. So that's this piece. So the purpling of the ventricles just before the ventricles contract, we can see that with our electrical leads as the QRS complex. Now, you might notice, well, how come this is shaped like this and this is shaped like this? Well, because the spread of that depolarization across the atria is sort of broad and flat. So we see it as sort of a bump or a smooth curve. In the ventricles, because there's this conducting system that moves signals so fast, the ventricles contract very quickly because they have this sort of built-in wiring system to do so. So the QRS complex is always very narrow. So even though there's a lot more cells represented here, because of that conducting system, the signaling happens much faster. And then the T wave we don't have in our picture, but as this purpling reverts to its baseline, we can see that with our electrical meter too. So technically speaking, this is the T wave. As the purple disappears and it goes back to its normal state for the ventricles, we see that as the T wave. So one of the things I definitely want you to know about the EKG is what each piece means, right? Okay, so the P wave is atrial depolarization, right? The QRS is ventricular depol, right? So depolarization. And then the T wave is repolarization. So as you know, when you depolarize a thing, you take it from a membrane potential of like minus 90 and you flip it up to plus 30. Well, when you push it back down to minus 90, we call that repolarization. So the T wave is ventricular repolarization. Now, why don't we see atrial repolarization? Because it's buried in here. Because there's so much more ventricle mass than there is atrial mass, we don't see atrial repolarization on the EKG because there's so much other stuff happening in the ventricle that it just gets buried. Otherwise, we would see a ventricular or an atrial repolarization after the depolarization. All right. So P wave, QRS, T wave. So atrial depolarization, ventricular depolarization, and then the T wave is a ventricular repolarization. Okay. So you should know each of these parts. I don't care if you know the intervals, like the PR interval, ST interval. If you were to take a class on EKGs, those intervals are hugely important, and they get studied, and they tell you a great deal about the health of the heart. But for us, we're just going to stick to the P, the QRS, and the T, and what each piece represents in the heart. All right. So before we can get into how does this action potential or these electrical changes, how do they become contraction, we need to look a little bit at the difference between, or one of the differences between skeletal muscle and cardiac muscle. All right, so some of this should ring a bell from last semester, but in skeletal muscle, we have this concept of a twitch. In other words, if you stimulate a skeletal muscle just once, what happens? Well, we get a pattern like this. So if we send a signal to this skeletal muscle, it depolarizes, so the cell membrane goes from -85 up here to +30. And the response to that depolarization is calcium is released from the sarcoplasmic reticulum, right? And then calcium triggers muscle contraction because it moves that tropomyosin away from its binding site on actin. All right, so what we see is we get a stimulus followed by a brief, short contraction. All right, so that's skeletal muscle. In cardiac muscle, there is no stimulus, right? Because the brain and the nervous system doesn't stimulate the heart to contract. It does that all by itself. So what we get is a very different pattern between the electrical activity and the contraction activity. All right, so in skeletal muscle, we get an action potential followed by a twitch. In cardiac muscle, we have this action potential that has this very strange shape, right? Instead of being sort of short and fast, like we're used to seeing in nervous tissue and skeletal muscle tissue, in cardiac muscle, we have this broad, flat part right here called the plateau. So what we see is, as this action potential proceeds, and it proceeds sort of over time as opposed to in a short amount of time, and if we look at the contraction sort of follows along behind it, right? So the cell membrane depolarizes, and then as it sort of drifts here towards zero, that's when we start to see contraction happening. And we'll see why that is in just a minute. So we have a quick action potential in skeletal muscle followed by a fast contraction, whereas we have this long, drawn-out action potential in cardiac muscle, and we have this sort of slow, long contraction and relaxation. So the contraction builds and builds and builds, and then it sort of relaxes, and then it's ready to do that again. All right. So what about this action potential? What is it showing us? Well, we can divide it into 3 phases. Okay, the first phase, the rapid depolarization, that's this quick upstroke. This is virtually identical to what you'd see in a neuron or in a skeletal muscle fiber, because it works in the same way. And that is sodium channels open, and because there's a huge difference in concentration of sodium outside the cell versus inside the cell, if you open a sodium channel, sodium comes rushing in the cell. And because sodium carries a positive charge, as all those pluses come rushing in, the cell membrane potential flips from minus to plus because all that charge has come in. So that is what we see here, this first piece. We go from -90, boom, up to +30. Same mechanism that we see in an action potential in a neuron or an action potential in a skeletal muscle. All right. So this membrane potential change in the cardiac cell then triggers a second event, and that is this plateau phase. So when the membrane depolarizes, calcium channels open. And calcium is also much higher on the outside of the cell than it is on the inside. So once those once those calcium channels open, calcium starts to enter the cardiac muscle cell. So that is what is happening during this plateau phase right here, is calcium is coming in from the outside. Now this is a spot where skeletal muscle behaves differently than cardiac muscle does. In skeletal muscle, calcium is stored inside the cell, right, in that sarcoplasmic reticulum. So when there's an action potential, calcium is released inside the cell to other parts inside the cell. Well, for cardiac muscle, it's a little different. Calcium comes into the cell from the outside, and that calcium entering then triggers the release of additional calcium from the sarcoplasmic reticulum inside the cardiac cell. So we have a little bit of a different process. But we know, because cardiac and skeletal muscle share the same kinds of muscle fibers, calcium triggers contraction in skeletal muscle. It also triggers contraction in cardiac muscle. So once calcium is present there in the cell, the cardiac cell is going to start to contract. So in this plateau phase, we have calcium coming in, and that calcium is what's going to trigger the contraction. So, like in our picture here, plateau phase, calcium is entering, and as calcium enters, look at what happens. The contraction starts to build, right? And then the relaxation starts to happen just about here when the plateau phase is ending. And that's because the calcium channels are closing. And as the calcium starts to disappear, the cell starts to relax, right? Just like you'd see in a skeletal muscle cell. All right, so that's the plateau. And then the last phase is repolarization. And here again, it happens very similarly to how we see that phenomena in nerve cells and muscle cells. So sodium channels make a quick upstroke, and then as potassium channels open, we see the cell going back down to its baseline membrane potential of -90, right? All right, so the cardiac muscle action potential, this is the butter zone right here, so to speak. The opening of calcium channels allows calcium in, and it's that calcium that then triggers the contraction that is what we need to have happen. All right. Okay, so the SA node of the conducting system is the typical pacemaker. So it's the region of the heart that's going to trigger that repeating beat pattern. So the SA node can be sped up or slowed down. And the principal ways that is done is by using the autonomic nervous system. So the sympathetic nervous system, the fight or flight system, it can speed the heart up. That's down here. The parasympathetic nervous system, the rest and digest system, it can slow the heart down, which is right here. And all this slide is really telling you is that the way that the heart is sped up or slowed down is by changing the resting membrane potential, right? So here in the normal heart, we go from minus 60 is where these cells sort of sit most of the time. And then at about 75 times a minute, they beat and cause the heart to beat, and then they go back and relax again, and then they beat again. So you can slow this area down, so slowing the heart rate down, by moving that resting potential down. So see how under parasympathetic stimulation, instead of coming back to -60, it comes back below that, to -70, let's say. And that just means it takes this area longer then to get to that threshold that causes an action potential to begin. And then for the sympathetic system, it's just the opposite. Under sympathetic stimulation, the cells of the SA node, instead of coming down to -60, they sort of come down to like -50, so they depolarize faster. So the way that this pacemaker works is it's sort of a leak. So the heart or the cells have an action potential and they repolarize. But instead of staying at -60, these cells leak sodium. So the sodium is leaking in, and then eventually that brings the membrane potential up above its threshold, which then triggers that whole series of events like we saw in nerve cells last semester. All right. But of more importance, I think, than understanding how that part works. What's the take-home message from this slide? The sympathetic nervous system speeds up the heart. The parasympathetic nervous system slows the heart down. And it does that by changing the resting membrane potential. So making it more negative slows the heart down. Making it less negative speeds the heart up. All right. Okay, stroke volume. So that's over there, right? Cardiac output is stroke volume times heart rate. Right? Stroke volume is the amount of blood that leaves the heart in one beat. Right? All right, so what does that mean? Like, how do we calculate that, or how do we see that in motion? Well, one of the most common ways to think about this is the heart is, in fact, a pump. Right? So we can think of it as a pump. So we have our pump here, our water pump, right next to the heart so we can see sort of what's happening. All right. So in order to pump water, first you have to get water into the pump, right? That is what we call ventricular filling, which happens in this first phase right here. So the heart is relaxed. The atria are relaxed. The ventricles are relaxed. The AV valves are open. And the aortic and pulmonary valves are closed, right? Because we don't want blood flowing backwards during this process. So the exit door, so to speak, from the heart is closed. So as blood returns to the body and returns from the lungs, it's going to fill the ventricles. It's no different than in our water pump. When you pull the water into the pump, like we see here, you're filling it up, right? And that's the same thing. So in diastole, the heart is filling. So now, once we've got the pump full, okay, now we're going to want to move water with it, right? So we get ready to push down on the pump and move the water. Well, there we have our first sort of measure that we calculate stroke volume from, and that's the EDV, end diastolic volume. All right, sounds complicated, but it isn't if you look at the words. Diastole is a period of time, right? It's the time the heart is relaxed. So if the heart is filling while it's relaxed, it's going to stop filling when the heart starts to contract, right? Because as soon as the heart starts to contract, the AV valves close, and that's the end of filling. The heart isn't going to get any more blood in it that cycle. So the end diastolic volume is the amount of blood in the heart just before it starts to contract. The end diastolic volume is also the largest the ventricles get during the cardiac cycle, because they're as full as they're going to be. So just like our pump here, it is at its largest when it's fully been filled. You pull the handle up, and eventually you put all the water in the pump that the pump will hold. That's the end diastolic volume, right? So the most blood that's in the heart before it contracts. So what happens then? Well, the heart contracts, right? We're going to pump that blood. We're going to push the blood out of the heart and out into the system. So in our water pump example, we filled the heart, EDV, and then we're going to pump it all the way out. All right, so the heart contracts. At some point, it will reach its smallest size. In other words, in that beat, the heart will have contracted to its smallest, right? And we call that the end systolic volume. So at the end of systole, in other words, at the end of the ventricles contracting, how small did the heart get? So to use our pump example, if you push the handle all the way down as far as it will go, the amount of water that's in the pump is the end systolic volume. In other words, it's what remains in the heart, or what remains in the pump after you've pumped as much as you can pump out. And our hearts are not perfect pumps. In other words, they don't empty. The heart never empties. Okay, so the only way to determine how much blood actually left the heart is to measure the amount of blood that was in it before it started to contract, and then you subtract the amount of blood that's still in the heart at the end of its contraction. And the difference between those two is the amount of blood that actually left the heart, the stroke volume, right? So stroke volume is end diastolic volume minus end systolic volume. The amount of blood at the beginning of the contraction, and then minus the amount of blood at the end. Okay, two very important terms because we're going to see in a minute or next time how various variables and factors affect these two factors. And because stroke volume is part of cardiac output, any change to end diastolic volume or end systolic volume is going to change cardiac output. So it's going to change how effectively or how much blood the heart is able to move around the system. Okay? So two important terms, EDV and ESV. All right. Okay, so stroke volume is affected by anything that affects EDV or ESV. So, for example, if we took end diastolic volume and we did something that made it go up, in other words, we increased end diastolic volume, we're going to increase stroke volume, right? Because essentially we made our pump bigger. If there's more blood in the heart before it starts to contract, well, that means if it gets to the same small size, we've increased the amount of blood it's pushed out. Likewise, end systolic volume, if we were to increase that, let's say, so the heart isn't able to empty as much, we're going to reduce stroke volume and cardiac output because of the effect of this equation right here. So, for example, end diastolic volume, venous return. Okay. Venous return is simply the amount of blood that returns to the heart before its next contraction. So one of the things that affects end diastolic volume is as venous return goes up, end diastolic volume goes up. In other words, this sort of is very intuitive. The more blood that comes back to the heart, the fuller the heart's going to be before it contracts, right? Well, that fullness is the end diastolic volume. So, if we increase venous return, we increase end diastolic volume, that increases stroke volume, right? Which then increases cardiac output. So, the more blood that comes back to the heart, the more blood the heart pumps out. So that's one. Preload. Really, preload is just another way of saying the same thing. In other words, if we load up the heart extra big and full before it contracts, then it will actually pump out more. All right. So what about filling time? Filling time is the amount of time that there is for the heart to fill before it contracts. So this is directly related to heart rate. So the faster the heart beats, the less time there is for the heart to fill before it contracts again. Right? That sort of makes sense. You know, if a thing is moving very fast, there's less time in each piece, okay? So, you know, when your heart is nice and relaxed and, 50 beats per minute, let's say, the filling time is very long. In other words, there's lots of time for the heart to fill. But let's say you've been, sprinting, and now your heart beats 170, right? That's going to reduce your filling time because the heart is contracting so fast, there isn't as much time for it to fill up. So a decrease in filling time causes a decrease in end diastolic volume. So what does that mean? Less time to fill means less full heart. A less full heart means less stroke volume because the heart, you never got all the water in the pump. You're pumping so fast that you didn't get the handle all the way up to the top. So as that goes down, and then cardiac output also goes down. All right? All right, so a number of factors that affect EDV. All right, well, what about ESV? The primary ones are the primary two. The first one is contractility. Our hearts are far superior to a pump that you can go buy at Home Depot. And one of the reasons for that is our hearts can work better depending on how well we need them. So, for example, when the sympathetic nervous system, so the SMS, the fight or flight system, when it's active, it increases the effectiveness of the heart. So what it does is it causes a decrease in end systolic volume. So when we're in that fight or flee response, our hearts actually contract stronger and better. So at the end of contraction, there is less blood in it under the influence of the sympathetic nervous system. All right, so what does that mean? Well, if we have the same end diastolic volume, but we have less of an end systolic volume, so the heart got full, but then it squeezed extra hard, so even more blood got pushed out that beat, we're going to see an increase in stroke volume, right? If this term goes down, this term should go up because we're subtracting less, right? So contractility decreases end systolic volume, that increases stroke volume, that increases cardiac output. So a change there, or a change in the end systolic volume affects cardiac output. Okay. And then the other one that affects end systolic volume is afterload. Okay, well, what does that mean? Afterload is the pressure the heart has to pump against just to start moving blood, right? So there's already pressure in the system all the time. So in the aorta, right, what's going on?
I'm sorry, there was a cricket that just like jumped.
It's
back
huge.
at me, like this big, and it keeps
jumping on
her. I don't do cricket.
He's not going to eat much.
It's in her bag. It's in your bag. In my bag. It's, yeah. Sorry, I'm gonna tell you afterwards.
That's all right.
Oh my gosh, it's right there.
You see it?
Yeah. Okay, did you get it? No.
It's huge.
It is huge. Yeah.
Right.
I tried to step on it and it just flew away. Just let it muffle away.
Yeah. You become the star of the
I
crowd.
know.
All right, let's. Okay.
Well,
Afterload. He's just going to hang out there and listen, I think. What is afterload? So there's already pressure in the system. So in the aorta and the pulmonary trunk, there's pressure all the time. So in order for the heart to actually push blood out of itself, it has to push against these pressures. So that is afterload, the pressure the heart has to push against. And what it has a tendency to do is it increases end systolic volume. That means the heart doesn't get as small, it doesn't contract as completely because it's having to push so hard against something that it can't. So one of the classic ways that we see afterload is an increase in diastolic blood pressure. So you know, we have blood pressure 120 over 80, right? The lower number is the diastolic. As this number goes up, so let's say we have 140 over 100. The higher the diastolic pressure, the higher the afterload, the greater the end systolic volume, the less the stroke volume, the less the cardiac output. So if you have a person who has a high diastolic blood pressure, you're going to encounter that phenomenon. Okay. So affecting ESP is contractility, which decreases it, and afterload, which increases it. For end diastolic volume filling time, as it goes down, end diastolic volume goes down, so cardiac output goes down. Venous return is preload. So the greater the amount of blood coming back to the heart, the more it pumps out because it gets fuller at the beginning. And then one that involves both of those is what we call the Frank-Starling relationship. And this, again, it makes our hearts far superior to some pump you can buy at Home Depot. And it goes like this. As the end diastolic volume goes up, it makes the end systolic volume go down. Now, why would that be? Our hearts work best when they get a little stretched out. You know, it has to do with sarcomere and muscle length. You know, that when a muscle is just its right length, it has its maximum strength. Well, for our heart, we don't really get to that point until the heart is a little stretched out at the beginning. So we call this the FS, the Frank-Starling relationship. And what it's saying is, the fuller the heart is at the beginning of a contraction, the smaller it will get at the end. And what this does, this relationship, results in a dramatic increase in stroke volume. Because if we increase this term, but decrease this term, we have sort of a double effect, right? We're making a bigger thing minus a less small of a thing. So we end up with a much larger stroke volume and a much larger cardiac output. All right, so, well, I know complicated stuff here today, but factors affecting stroke volume. So why should we care? Because cardiac output, blood pressure, you know, is what makes blood go around the heart, is cardiac output times total peripheral resistance. So, we'll talk about that more later. But the reason that these stroke volume factors matter is because eventually they factor into blood pressure. So when you go from relaxed, like you are now, to jogging, one of the things that's going to change is the end-diastolic volume and end-systolic volume. So your EDV is going to go up, your ESV is going to go down. That's going to increase your cardiac output, which is going to sustain your blood pressure despite having more blood doing more things. So they're important factors because of how they affect other things. All right. All right, let's do some questions and call it a day. All right, the normal pacemaker of the heart is located where? In which of those things? Where did our little cricket friend go? You hate to just stomp on him. Because he's a little living thing, just like all of us. All right, is that everybody who's going to answer? All right, the correct answer there is B, sinoatrial node. So the SA node is where things begin. The AV node is in the middle of the heart, and its claim to fame is there's a delay associated with passage through the AV node that allows the atria to contract before the ventricles. All right. The P wave of the EKG is a signal from which of those events? Well, I got to end this one early because we're out of time.
None of the answers came up on.
Huh?
None of the answers came up on either.
They didn't come up. All right, so the P wave is not depolarization of the SA node. A lot of people would put that. That is not true. It's the depolarization of the atrial tissue itself. So don't get tricked by that one. All right, thank you, everybody. I will see you on Wednesday.